To construct our RC circuit, we started with a 6-volt battery, a capacitor, a resistor, a voltmeter, and a stopwatch. To connect them, we took the green wire and attached it to the positive end of the battery. We then attached the other side to the long end of the conductor that is also positively charged. Next, we took the second green wire and connected the capacitor in series with the resistor by attaching one end to the negative side of the capacitor and the other to one side of the resistor. Then we connected the black wire that would be connected to the negative terminal of the battery to the other end of the resistor. To measure the voltage drop across the resistor, we used the white wire to connect the black negative terminal of the voltmeter to the side of the resistor connected to the capacitor. We then used the yellow wire to connect the red positive terminal of the voltmeter to the other side of the resistor. Right after we connected the black wire to the negative terminal of the battery, we took photos of the voltmeter and timer to see how the voltage was changing over time. When we first connected the circuit, the voltage dropped quickly. After some time passed, the voltage continued to drop, but not as quickly. We plotted our data on a time versus voltage graph and connected the points using a line of best fit. The graph shows voltage decreasing at a decreasing rate until both the voltage and change in voltage approach zero. This suggests that V varies with some constant value raised to the negative t. To find the line of best fit for our time versus voltage graph, we graphed time versus natural log of the voltage. We then drew a line of best fit, which in this case is linear. The equation for the line of best fit of the time versus natural log of V graph is y equals negative 0.07x plus 1.8. Because in this graph y equals the natural log of V and x equals time, we can use this equation to solve for the time versus voltage graph line of best fit. To solve for V, we raise e by both sides of the equation. E raised to the power of ln V equals V. E raised to the power of negative 0.07t plus 1.8 is equal to E raised to the negative 0.07t times e to the 1.8. E to the 1.8 approximately equals 6, so we find that the equation for the line of best fit of the time versus voltage graph is V equals 6 times e to the negative 0.07t. To calculate the resistance of our resistor, we start with these three equations. Substituting CV for Q, the C's cancel, and we are left with delta V is equal to the EMF times 1 minus E to the negative T divided by RC. We can now set both delta V equations equal to each other. Solving for Vt, we find that Vt is equal to the EMF times E to the negative T divided by RC. This equation resembles the equation we found for the time versus voltage graph from our data. The EMF of the battery is equal to 6. We can then set negative 1 over RC equal to negative 0.07, the slope of the time versus ln graph. Solving for R, we find the resistance of the resistor to be about 14,000 ohms. The colors on our resistor are brown, black, orange, and gold. This means that the resistance is 10,000 ohms with 5% uncertainty. Our resistor, however, is 40% higher than the anticipated value and thus disagrees with the printed value of the resistor. The internal resistance of the battery was not accounted for and could be the reason for our higher calculation. Other possibilities for error may include the many possible variations of the line of best fit and speediness in pressing the timer when the battery is connected.